Hello, this is Andrew and Zilong, and I'm going to talk a little bit about Gödel's incompleteness theorems. So first, before we actually start into actually talking about these theorems, we have to lay down a set of baseline definitions. First is the idea of an axiom. And for us and in mathematics, this is just generally a statement that we accept as true. We don't need to sort of prove it, we just sort of know that intuitively or just by the way that the system is built, that this is something we accept as true. And we can use them as building blocks for other proofs. As an example, if we take two axioms, say for example, the number 1 exists, and a number is equal to itself, we can use these two axioms as building blocks to prove the statement that 1 equals 1 is true. And we can prove it's true because of the axioms. Next, we're going to talk about the idea of completeness. So in a complete axiomatic system, an axiomatic system just being a system like what we just described that uses those axioms as building blocks to prove everything else, all statements can be proven true or false. This means that every single statement, you can use those axioms to either say that yes, this is definitely true, or no, this is false, and the negation is true. Lastly is the idea of consistency. So in a consistent axiomatic system, there are no statements in the system where both itself and its negation are true. So for example, 1 exists and 1 does not exist, both being provable in a system would make it inconsistent. And the reason why we really don't like inconsistency is because if you can prove, say for example, 1 exists and 1 does not exist, then by the explosion principle, you can really prove anything in your system. So your system, in effect, really becomes something that you can't really use to reliably prove anything. So, with those sort of baseline definitions in place, let's start talking a little bit about that first incompleteness theorem. So in any consistent formal system, F, within which a certain amount of arithmetic can be carried out, there are statements of the language of F which can neither be proved nor disproved in F. So you can sort of see some of the language we just talked about, like consistency and the idea of proving nor disproving something. So to simplify this down, essentially for a system that is sufficiently expressive, so our modern mathematical system would be an example of such a system, there are statements that can't be proven or disproven because we want to assume that it's consistent. In fact, one other interpretation of this first incompleteness theorem is that for this given system, it has to be either inconsistent or incomplete. And so let's think about how this theorem actually came to be. And you can sort of see the statement on the left as that first indicator. This statement is false. So in something like the English language, these sort of self-referential statements can create paradoxes, in that if we think the statement is true, well then it's saying it's false, so it can't be. Whereas if we think it's false, well then in fact the statement inside there is true. So we have a statement here that's either true nor false. And so for Gödel, this was a really important concept in formulating that first theorem. But he had to overcome the hurdle of actually applying English to mathematics. And the way he did so was using something called Gödel numbers. So each symbol in mathematics, which we sort of use to derive all these mathematical statements, he assigned a number, which you can sort of see on the right. And so one example here is that, so if we have a statement 0 equals 0, well that would be the numbers 6 for 0, 5 for equals, and then 6 again for 0. Then, using prime numbers, each one of those statements got back to a unique Gödel number. So we can see 2 to the power of 6 for that 0, 3 to the power of 5 for that equals, and 5 to the power of 6 for that last 0. That creates that unique Gödel number. And so with this in mind, Gödel has now created a way for all of these numbers to be uniquely represented as sort of the numerical representation of statements. So, with this in mind, he actually used the statement, "This statement cannot be proven." And this is what's called a Gödel sentence. So we have a bit of an issue here in that now we've introduced into our mathematical system one of these sort of paradoxes, which is that if the statement is false, then we have a false statement that can be proven, which means that math is inconsistent. But if the statement is true, then we have a statement that we definitely know is true, but then it's not true due to our axioms because, well, it can't be proven. So in that option, math is incomplete. And since an inconsistent math system really can't be reliably used to prove anything, we'd take to prefer incompleteness over inconsistency. And that actually concludes how Gödel proved that first incompleteness theorem, that our system cannot be complete, and there has to be statements that are neither provable nor disprovable. So, with that in mind, I'd like to pass it off to Andrew to talk a little bit about the second theorem.
Thanks, Mrs. Long. We will now look at the second incompleteness theorem, which states that a consistent formal system with sufficient elementary arithmetic cannot prove its own consistency. The original proof outlined by Godel for the second incompleteness theorem is complicated, so we will present an alternative proof that hopefully still gives intuition on the fundamental logic behind the claim. It looks very similar to the proof of the halting problem, with some small changes. First, we can compare this with the halting proof. Notice that instead of running t on t to determine if it halts, we instead are looking for a proof to determine if it halts. Now, consider t fed into itself. If we find a proof that the program loops, then it will halt, and we can construct a step-by-step proof that it halts by tracing the code execution to the if statement and then to the halt. Vice versa, if we find a proof that the program halts, then it will loop, and we can construct a step-by-step proof of its looping. In either case of finding proofs, that means our math system is inconsistent since it has proofs for both halting and looping. Note that this doesn't mean our system cannot have an infinite loop or halt, but that it can't prove either of them. If any of these if statements trigger, we are essentially poisoning our system for inconsistency. In summary, if our system is to be consistent then, both cases of loop and halt should not be provable. Side note, this is the first incompleteness theorem. However, here is the key insight. If both if statements in this program never trigger, which would occur if our system is truly consistent, we would infinite loop, since there are an infinite number of proofs. I repeat, if our system is consistent, we would infinite loop since both if statements result in inconsistency. Importantly, consider that if we could prove f is consistent within f, that would be a valid proof that t on t infinitely loops, which would trigger the first if statement, and then making it inconsistent with a contradiction. We can conclude that if f is consistent, it cannot prove its own consistency. Now the implications. The foundational math systems we use are incomplete and they cannot prove their own consistency. I think, honestly, the implications are a bit self-evident as mathematicians ourselves. Completeness and especially consistency are implied of math since we begin learning it. How can we expect a statement to be false and true at the same time, or that we cannot prove a statement? However, let's go over some interesting implications anyways. Long-standing unproven questions like the twin primes conjecture, which is that there are an infinite number of consecutive primes, or Goldbach's conjecture that every even whole number greater than 2 is a sum of two prime numbers, may not have proofs even if they are true. For the consistency aspect, larger math systems can in fact prove smaller ones are consistent. For instance, the Zermelo-Frankel axioms of set theory, which serve as the foundation of much of math, can prove that the axioms for non-negative integers, that 0 exists and that every integer has one predecessor, are in fact consistent. But then, what if the Zermelo-Frankel axioms themselves are inconsistent? Our whole system would be kaput. This goes into a deeper thing of that we can never prove our systems are truly consistent, since such a proof would destroy their own consistency in the first place. And thank you for listening. I had a fun time researching this.